Welcome to the video on Ito's formula for Brownian motion. So what we have already discussed in the introduction is that if we have such an Ito integral, which might be suitable for applications in finance, we cannot expect that it fulfills the classical fundamental theorem of calculus. And Ito formulas is the corresponding formula for the Ito integral. Right? So what we are going to prove today in this video is, so this is in chapter 3.3, the lecture notes. And the main goal of this chapter is theorem 3.18, which is Ito's formula. Later in the course, we will also prove more general Ito formulas. This is the Ito formula for Brownian motion. And in some sense, it's the most simple Ito formula we will see. So let me give you directly the statement and then comment on this. So for a function which is twice continuously differentiable, we have that if we look at the function applied to the Brownian motion at time t, this is equal to the function applied, evaluated at time 0, or at 0, because this is, go to the Brownian motion at 0, plus the integral from 0 to t of the derivative of the function f applied to the Brownian motion at time s, integrated with respect to ds, plus 1/2 the integral from 0 to t of the second derivative applied to the Brownian motion at integrated with respect to ds. And this holds for all t, p almost surely. Okay, so let me comment on this. So first, this is here a well-defined integral. Right? We know that this is in h2 log, so we know how to define this integral. So that's great. This is well-defined, and I mean, since the function f is in C2, this is a continuous function here, so this is a continuous function. This is a classical Riemann-Stieltjes integral. So all the integrals involved here are well-defined. That's great. And what's hidden here is, again, the quadratic variation of the Brownian motion, right? So there's a nice ds term is because what we have here, the Brownian motion. We are lucky that the quadratic variation is just the identity function. Okay. So we have a well-defined formula, which we are going to prove now. Right, and we will see later more general ones. Okay, so so what I just said is also like the content of remark 3.19, which I'm not going to write down here, as I just already said. Okay, so let's come to the proof, which is the main work in this video. And first thing I want to do is it's enough to show Ito's formula for a fixed time t. Show Ito's formula for the fixed t in 0 to t. Right? Because both sides are continuous. So what we show, what we have seen is that if we have modifications, if the right-hand side and the left-hand side are modification of each other, then they're indistinguishable. This means they're identical. Then it follows. It holds for all t p almost surely. Right? This is the problem sheets. Oh, I think one of the. Okay, so it's enough for me to consider a fixed t, and then because both sides are continuous processes, we can extend it immediately for all t. All right, step one. I think this is the main important observation here, is how to decompose the difference of the Brownian motion applied to the function applied to the Brownian motion at time t and f0. Okay. Okay. As before, right, we have fixed my t, and I want to set the ti as before. Well, I take a uniform, equidistant partition of my interval 0 to t. Okay, so this runs from 0 to n. Okay, and now let's decompose the difference of the f applied to the Brownian motion at time t and minus f. First thing is we use a telescoping argument. So we write it as a telescope sign along these ti's. Right, so that's the first idea. Right, and the second main idea is to use a second order Taylor expansion. So when we expand this function f around the point bti minus 1. Okay, so this is our first derivative. Plus 1/2 second derivative. Well, then I get here a square. Plus, okay. Plus remainder term. Right? If we do a second order Taylor approximation, we have an error term or remainder term, which you need to understand. Right? So this is my second order Taylor expansion of each summit. Okay. So, well, so we have now 3 terms which we need to understand. And actually, I mean, it's not surprising if we know what we want to get in the end. If you compare this, well, the first term, this an term, will go to our e2 integral, as we expect. The second term will go to the, here you see already the quadratic variation popping up. So this goes to the integral with respect to the quadratic variation, which is just the ds integral here. And the remainder will go to 0, which is good. Okay, so okay, let me give you also what this remainder term is. So R is the remainder term of the e2 integral, which, for example, is given by the integral from x to y. So the x and y are 2 points in R of y minus u. And this is mean value theorem, which tells you this is a suitable remainder. Remainder of the Taylor approximation. No expansion. Cool. And now I can rewrite it by using a substitution. So let's set u to be x plus t multiplied with y minus x. What do I get? I get x minus 1 squared, and the integral from 0 to 1 of t minus 1 minus t of f, the double prime of x plus t minus second derivative applied to x dx dt. So why do I want to have this substitution? Well, what you see is if I plug in now the Brownian motion, and here's a mistake, or at time ti and ti1, I get again here the quadratic variation, because I get here the square increment of the Brownian motion at time ti and ti minus 1, and some term which goes to 0. That's the whole goal. That the main point here is, okay, do you see here they exist? Ah. So, okay, wait, before I go on, let me make one assumption. Let us assume for a moment, say step 1 to step 4, that f has compact support. I mean, this is just means that the function is bounded. That's actually the main point. Support. Right, and then in the fifth step, we will use a localization argument to extend what we have shown for this f. So this is a procedure which we do all the time. The point is, well, if we assume this, we have that this remainder term can be estimated by, well, the difference of x and y squared times a function h, which is continuous. Oh, okay, I don't. For h for some continuous and bounded function h from R2 to R with is 0 on the diagonal, right? So cool. All right. So now let's come back to the terms a1, an, and b, bn, and cn. Right? And we assume we work under this assumption here that f is compactly supported, and then we extend it. All right. So step 1. Sorry, step 2 is an goes in probability to the integral. In probability. Okay. Well, that's fine. True. By what was the theorem 3.17, which is telling you what the Riemann sum approximation here of a continuous function, and f prime is continuous, converges to the integral. So right, this is what we have already shown. Maybe I should add as f prime is continuous. Okay, that was easy. Well, it was not easy, but we did already all the work. Step 3 is Bn goes to 1/2 the integral with respect to the quadratic variation, respectively here just ds. right? This. Cool. As again in probability. Okay, here we have to work a bit. So first, note, well, we can represent Bn as sum, or 1/2 the sum of the second derivative applied to the Brownian motion at ti minus 1 multiplied with the increment t minus t in time. And all right. That's a bit, okay, let me write the new line so it's not too squeezed. Plus 1/2 of the same sum. So we add a 0 here, right? So we have here still the actual sum Bn. That's not a definition, this is the quality of the square increments of the Brownian motion minus square increments of the Brownian motion, right? Cool. Now we give these names again. So this is Bn1, and this is my second sum, Bn2. Okay, and for the first sum, this goes already to the right term. And so since also f prime is continuous and Bt is in any way, I mean, it's by definition of a Brownian motion is continuous. Are continuous. And this is a classical Riemann sum approximation of the Lebesgue-Stieltjes integral. So this is nothing else than the Lebesgue-Stieltjes integral of f prime applied to the Brownian double prime, the Brownian motion at time s ds. This solves. Right? Here's nothing to do. And this is. So we have to show that the second term goes to 0, but this is actually what we believe because we know that the here the square increments approximate the time. So this is, you could run a different argument as well by looking directly at the conversion of the quadratic variation. But let me give you a more elementary one. So this is the first observation. The second one is, okay, we want to show that the Bn2 goes to 0. And okay, we want to show it here in L2. Right? If you choose the right object, which makes your life easier. All right. So if we have here the square, well, what we get a lot of terms. So first we get the 1/2, gets the 1/4 because we squared. And now we have a sum, a double sum of ji 1 minus from hij from 1 to n of the expected value of second Brownian motion, the sector applied to the Brownian motion. So then the square increments here. So ti minus 1 squared minus ti minus 1. And now we have this multiplied with the same in j. T minus 1 and then tj minus 1. Right. Now we have enough brackets. Cool. Okay, and now, okay, what do we know about the Brownian motion? We know it as independent increments. of B. Then, well, this means all the off-diagonal terms disappear. Cool. So we end up with the sum only over 1 per index I of everything which is in the diagonal. So this is f double prime square multiplied with all this increment squared. So let's this I. So this is only the terms where I is equal to j are still there, right? This means we get these sums all squared. Yeah. Anyway, this is a square and this is another. Okay. And now, okay, let's estimate. So we know that f double prime is bounded because we assume that f has compact support. So we can pull it out in the supremum norm. And, well, we get still the sum of the expected value of the quadratic increments of the Brownian motion minus the time increment, everything squared, and then the expectation of it. Okay. That's great because now we can just look at the distribution. I mean, we know how this is distributed, right? This is the distribution Ti minus Tji. Okay. Now, right. So this is just a certain moment, actually the fourth moment of a Brownian motion. So, well, you can look it up on Wikipedia or calculate it yourself what the fourth moment is. So what you get here is twice. So you lose 1 over quarter. You have your supremum norm of the second derivative. And then you have here just Ti minus Ti is 1. If I recall right, we have done such a calculation. We should calculate it in more detail at some point. So let me not do it again here. Or you just look up the increments here. The moments of the normal distribution. Cool. But I mean, right here, this square increments of the time difference goes to 0. Okay, let me mark it. This here. The fourth moment is 3 times the time, the square. Right. So actually, I give you in the lecture notes some more details, but this is, I think, what you can check yourself. And you can even look it up. All right. Yeah, no, this is what you can look up, and then you can maybe, okay, wait, let me. You can look it up. All right. Long story. This means the Bn2 term goes to 0 as n goes to infinity in L2. And this in particular in probability. Such in probability. All right. Step 4. Step 4 is we want to show that these remainder terms, or the sum of the remainder terms of the Cn's, go to 0 if n goes to infinity as the probability. Okay. So again, we assume that f has compact support. So let us estimate the L1 norm. Okay, I mean, here we need to, just need to be smart which norm we want to estimate, because L1 norm will also ensure what we want to have. So let's estimate this. Right, and we know that we can have here the sum from I to n, and then we did this nice substitution, so we get now for x and y bti minus bti minus 1 square, and then the function h, and if you want, so in absolute values. Okay, all right. So how can we estimate this? Well, Cauchy-Schwarz seems to be a good idea. So let me Cauchy-Schwarz inequality. So we can pull out the sums. It's because they're finitely, it's a finite sum, we can pull it out without issues. And then we apply Cauchy-Schwarz. So we get here the fourth moment again, which we already have looked up. That's good. And then we have here the expected value of h applied to bj minus 1 to the power 2, and then 1/2 of it. And here is minus 1 missing. Okay. So again, we know what this is. So we get 3. Right? This is, again, here, what we load up. We know the fourth moment of the Brownian motion now. So this is the square root from over here of 3. And then we have the sum from I to n of the ti minus ti, right? Fourth moment, and then you get here square, and the square is you lose because of the 1/2 here, times the expected value of h applied to bti and bti minus 1 square. Okay. All right, so we just need to handle this function h. But now, okay, we are h's. Since h is uniform continuous, we know that for all epsilon bigger than 0, there exists a delta greater than 0, such that for all x and y, right, this is, so if x and y are close to each other, so namely not further away than delta, we know that also h here, which is okay, it's on the diagonal 0, so that means, right, this is just 0. So by the continuity property, this is less than epsilon. All right. Hence, let's estimate h applied to b minus 1. So let's estimate this term, right? This is the term which is here. Let's forget the square root. If we can estimate the term, then we can also estimate the square root of it. So we want to estimate this. Well, okay. First, then we sneak an indicator function. So we sneak in an indicator function. And that's right. Right. Okay, that's cool. And we sneak in the indicator function that these b, the difference of the Brownian motions here, of the Brownian motion, so the increment of the Brownian motion is less than delta. Because if it's less than data, we can estimate this function h nicely by epsilon. And the second thing is, okay, well, if we sneak in this indicator function, we shouldn't lose anything. So we need to sneak in the complement of the set as well. So this is the complement TA BT minus 1 is greater than delta. Cool. And now we estimate this term. So, well, if this is true, so if we are on this set that the increment is less than delta, we can estimate h by epsilon, right? And then we get a square, so we get epsilon square. And well, the expected value of an indicator function is nothing else than the probability that this event happens. So this is less or equal than delta. Cool. And now let's come to the second thing. Well, the second term, okay, we can estimate h by its supremum norm. That's the brute force estimate. And we've lost a square here. So we get here a square as well. Cool. And well, then if again the indicator, the expected value of an indicator function, so we get the probability of this event, which is the event that this increment is strictly bigger than delta. Okay. That's great. Okay, now we can keep estimating. So this is okay, epsilon square is estimated by epsilon square, and the probability of some event can be estimated by 1. Here we go, just forget it. Okay, and then we have still the supremum norm of h to the square. And now we use Chebyshev, or actually Dupes maximal inequality, to estimate this y. Actually, Chebyshev is enough. Chebyshev inequality to estimate this probability by twice delta to the power minus 2 multiplied with the expected value of this square increment to the power 2. All right, that's great. Because again, we know what the second moments are of the Brownian motion, right? So that's simple to calculate. So we have here same as the line above. And now we have this. And this is nothing else than the time increment here from t to t minus 1. And actually, we also know what this is. This is nothing else than t divided by n. So what do we get here is n minus time t. Cool. So let's use this to estimate our Cn. Right. So we now we wanted to estimate the L1 norm of Cn, and we have now everything together, right? We estimate this by 3, the square root of 3, and then the sum of the increments, and now we can estimate also this expected value of h2, that's a square. So what we get here is Cn can be estimated by square root of 3, and then the sum from 1 to n of ti. You actually also know what it is, right? So right, this is again t divided by n. And then what do we else get? 3 epsilon plus epsilon to the power 2 of h. So the supremum norm of h. Delta to the power minus 2, n to the power minus 1, and some t, and this is all to the square root of 2, because, well, this is what we have here. All right, cool. So what does it mean? This goes to 3 times wait. So if we send, we want n send to infinity, right? If we send n to infinity, this all disappears, this disappears. But here we get some sums, so these are canceling, that's great. So this goes to 3 times sanity. All right, yes. Okay. And this holds for all, since epsilon was arbitrary, or is arbitrary, was arbitrary, and we get that indeed Cn goes to 0 in L1, and this means in probability. All right. And now, okay, we need to get rid of this extra localization where we said, okay, we assume that F has compact support, which is of course in general not true. So again, we introduce our standard sequence to localize, so tau m, which is the first time that the Brownian motion gets bigger than or less than m. T. Okay. All right. Yeah, as before, tau m are stopping times, right? We know these stopping times already. And we know that this whole space is just the union of all events that tau m at some point gets to, right? So this is the localizing sequence of stopping time. And then you proceed as before, right? So we know all m, there exists Cm, which is in C2 with compact support. Such that on this, as if we restrict Fm to the interval minus m to m, this is exactly the same as F on this interval. Right, then we can apply, so we have Ito's formula. Ito's formula holds for Fm by step 1 to 4. And then we can again, this means Ito's formula holds for F by using our theorem 3.3.1, which was the persistency of Ito integration, so that we can interchange local stopping times and with the integration operator. Yeah. And that's it. So let me give you one little example, which you have already seen, which is, okay, this is context example 3.20. So consider, for example, the function f to be 1/2 times x squared. And this is a function in C2. Oh, wow. That's good. And then we can apply Ito's formula. Ito's formula. we get, right, if you have 1/2 of the Brownian motion to the power 2 at time t, well, this is now nothing else than f applied to bt minus f0, because the Brownian motion at time 0 is 0. And the function is 0, and this is okay. Now E2's formula is telling me, okay, just to recall it, this is nothing else than the integral from 0 to t of f prime applied to the Brownian motion, integrated with respect to the Brownian motion, plus 1/2 integral from 0 to t of twice the second derivative applied to the Brownian motion with respect to its quadratic variations to ds. And now this is a simple function, so we can calculate the first and the second derivative. So the first derivative is just x, so that's the Brownian motion itself, integrated with respect to the Brownian motion. And here we have 1/2, and then the second derivative is just 1, so we get 1/2 multiplied with t. Yeah, and then this means great, right? So we have already seen that if we rearrange this, so if you look at 1/2 the Brownian motion times 2, right? This is a martingale. And at some point, we had an exercise where you had to show it by hand, which is, I think, a lot of work, but now it follows quite easily. This is a martingale. Right, and this is, I mean, you have shown this identity on the problem sheet, and you have also shown on the problem sheet that this is a martingale. So compared to the problem sheets. Cool. So let me conclude this video by giving you some, at least sketching an extension. So I'm giving you extension, but the proof will be only a sketch. Extension to time space E2 formula. All right. All right. So how does it work? So I want that my function f, which we allow to consider here in E2's formula, yep, this f, is allowed to depend on time directly. So what for this we need to deduce. So C1, 2, which is from 0 to t to r. Is denotes the set of all functions f from the interval 0 to tr2 to r, such that ft x is continuously differentiable in t, and tx is twice continuously differentiable. Maybe I should write like continuously differentiable. I'm not sure if this is a common shortcut, but you know what I mean. So it's in C2, and this is in C1 in X, right? So I'm twice continuously differentiable in space, meaning X, and 1 times continuously differentiable in T. All right, and then my E2 formula can be still recovered or obtained. This is theorem 3.21, and it's telling me, So this is ethos formula in space-time, let's call it, right? Because the Brownian motion takes some value in some space, and t is time. So for f in C1, 2, R2, this is, it takes values in R. Here we go. We have the Brownian motion and the f applied to the Brownian motion time t, and time t is equal to f0, 0 plus right now we have, I should not use. Okay, anyway, yeah. So okay, we have here the partial differential f ds integrated with respect to time. And now we have the stochastic integral where you have the partial differential of f with respect to x. Brownian motion. Then you have the second order term coming from the quadratic relation of the Brownian motion, which is the second partial derivative in x of f ds integrated with respect to s, right? For all t and 0 to t, p almost sure. All right. So the proof basically works exactly the same as before. I mean, okay, not exactly. I mean, you just need to understand how you this extra term this extra Lebesgue-Stieltjes integral with respect to time comes into play. So let me sketch a proof of proof. All right. So I'm not giving you the details. I'm just telling you, recalling basically the idea what we have done. So as before, idea. You have. We want to consider the difference here of these two terms, right? And you use your telescoping sum argument. Which means you have here f at time ti bti minus f at ti minus 1 bti. Right? Okay. And now, okay, this is okay. We need to. This is the new step. The only new step I think, which is in this proof, isn't coming now. So that's new. Is okay. We want to have an expansion in time and space, so we added 0. So let's do so. We have here ti bti, right? And now we have subtract. Right? You make the time step, go step 1 before, and now you have subtracted. I mean, so you add the 0, which is right, and this is the minus 1. Okay, right. So you added here the middle term in each sum. Right, and now what we do is we I'm running out of space. And what we do now is we do a first order Taylor expansion of the first term, which is right. And we do a second Taylor order expansion of the second term. So let's do the first term. So the first term is, okay, we keep here our sum of first term Taylor expansion in time. So what we have here is the derivative in time. Oh, sorry, I forgot the time dependency here. So ti at ti minus dbti. Now we have t plus some remainder which depend on time. Right, okay, this is, so this here goes here by a first order Taylor expansion. Cool. And for the second term, as before, use the second order Taylor expansion. So that's our second order. So okay. So the blue stuff is new, right? New. Right. Second order Taylor expansion. Right, and this goes here. Okay, what does it mean? Cool. Second derivative. Oh, okay, what's going on here? Sorry. This f ti b ti Brownian motion increments plus 1 square. This is now the second partial derivative in the second components in space, and the increments of square increments of the Brownian motion plus some the remainder term. Minus t, okay. Right. And now you do exactly the same as before. So what you see is if you send now n to infinity, the blue term, if I work with colors, I should do it in a smart way. So if you send n to infinity, what you get is the first terms, so the blue terms here go to the time derivative. Right, this is standard. This is again here the standard Riemann staircase integral, so there's actually not much to do. Yes, and then the green part is as before. And so this is the green part goes here, which is okay. First, I mean, this is as before, as in the same as we have done in last proof. This is second partial derivative, and the remainder terms go to 0, as you would hope for. dbt plus 1 square dp twice s. All right, so that's it. So I mean, you can really work out the details yourself, right? The only new thing is to, take care of this time dependence, which gives you another Lebesgue integral, which you know how to handle. And then you have exactly the same terms as you have seen in the last theorem of the simple E2 formula. So you know how to handle this, and the remainder term, you know how to handle all the terms. All right. Thank you for watching the video.